important to understand the attacks that we'll be talking about, so I don't want to blow over that too quickly. The third section will be the attacks on the fiber channel SANs. That will be the majority of our presentation, and then a conclusion. There are a lot of slides, if you notice in your slide deck. A lot of them are for reference, so I will be skipping through a lot of the slides, but I put them in the booklets just so you have some background material. All right, so let's begin with the intro. Before we begin, I'd like to ask a casual question to the crowd. How many people here use their home telephone number or their cell phone number for your banking password or your online or your ATM password? No one uses their home phone number or cell phone number. Okay. What if I told you, or what if you wanted to use your home phone number, but you wouldn't list it in the phone book? So you use your home phone number for your online banking password or your ATM code, but you don't put it in the phone book, it's unlisted. How many people would be comfortable then using their home phone number for all their passwords? All right, good answer. So keep that in mind. That's one of the major issues in storage area networks. We'll talk about that a little bit more, but keep that in the back of your head, how just because something isn't obvious, it's still easy to get. You know, someone's home phone number, even if it's unlisted, it's not in the phone book, you could figure it out pretty easily. You can figure out where they live. You know, I live in the Bay Area, so there's like 4 area codes. So of that 10-digit code, you know you can guess 3 of them right away. And depending on what county I live in, you can probably guess the prefix of the 7-digit code. So all of a sudden, what you need to guess is 4 or 5 characters, which is just a matter of time. So we all know, even though you can unlist your phone number, people can still get it relatively easily, as long as they're dedicated to get it. So in our introduction, we're going to have 4 bullet points and then comment about the importance of storage area networks. A lot of you may be asking, what are SANs, why are they important, and why do I care? So before we even get into the presentation, we're going to answer those questions right away. Some of your colleagues might have that question, or in the future, you might think about, wait, why did I care about this presentation? So let's go ahead and talk about that. What are SANs? SANs are basically large storage arrays that have good capacity, high availability, and scalability. If you have 100 servers, web servers, file servers, database servers, you don't need to put a disk drive in each one of them. You can have all that data, 80 gigabits, 800 gigabits, terabytes, petabytes, all back to a storage area network, which is usually run through a fiber channel connection. A lot of SANs can be fiber channel or iSCSI. Our definition of SANs today will be based on fiber channel only. What is storage security? Well, storage security is simply protecting the data in the SAN. The data, whether it's block data or file record data, it's basically protecting that data from unauthorized users. Whether that user is internal, a contractor, a consultant, someone in engineering trying to get access to HR, or an external unauthorized user, a hacker or a cracker. Why storage security? Why is it important? Why are we talking about it? Why am I up here preaching about it today? Well, storage administrators, and not just storage administrators, but statistically, a lot of storage admins have thought that fiber channel really is not a security issue. Security issues are only available and only pertain to IP. If I have a fiber channel SAN, I don't need to worry about security. I'm okay. Well, there's 2 reasons why they think that. Either one, fiber channel as a protocol, it's not a protocol, but as a medium of communication has gone through the due diligence of security and has security built into the frame, or they just assume that no one knows enough about fiber channel to attack it. Well, unfortunately, it's the latter. Many people assume fiber channel is secure, but they don't really know why. They just kind of say, well, it's fiber channel. I don't need to look at it. Who knows about fiber channel? It's an obscure technology. Now, that's not to say IP is easier to attack or more accessible to attack. I definitely do not want to come off and say, hey, all your fiber channel networks can be hacked tomorrow. That's definitely not what I'm trying to say. IP is still more accessible. It's easier to get access to. However, as you guys will find by the end of this presentation, a lot of fiber channel attacks are easier, or if not the same as IP attacks. But what happens is when you conduct a fiber channel attack, you'll have access to data. not just a username on a file server or a registry or a service. You have access to data. And that's why it's more critical than, I would say, a lot of IP attacks. And of course, when you have items such as intellectual property, source code, proprietary information, you can't use security by obscurity. We all know security by obscurity is not a valid control. And especially if you're using it to protect your sensitive data, it's just not acceptable. Just a quick slide. Most organizations that I've dealt with in the past, they spend more money and time and resources protecting web servers, which may have static marketing data, than their intellectual property and their SAN. Now, again, that's not an unexpected thing, but at the same time, a lot of people will have strong security organizations who are trying to protect the front doorstep of their organization, which is the website. But when it comes to intellectual property, they just assume things will be set up correctly by the vendor, which sometimes is the case, sometimes is not the case. One thing to consider is a lot of people in this room know about defense in depth. You have layers of security in the IP world. You have internal firewalls, internal access control lists, all these great things. But what happens is when you connect all those things to a SAN fabric, there is no segmentation usually, or the segmentation that exists is easily to subvert. So even though you have a DMZ environment, an application DMZ, an internal network, a management network, an admin network, if you're connecting all these things to one big fiber channel network, you're really creating a back plane for a flat network for people to attack systems from a DMZ environment to your internal environment. Why do I care? Data. If your data is classified as sensitive, or you think you have sensitive data to protect, then you should care. Now, you might find out that, hey, our fiber channel network, our storage area network is secure. The problems that we're talking about today aren't an issue for how our architecture is set up. And that's great. What happens, and the main reason why I'm doing this presentation, is a lot of people don't do that due diligence. They just assume. And you can't assume when you're talking about data. One particular thing is that a lot of questions I get is that, root or admin access is always attractive, but you don't need root or admin to access data in a fiber channel SAN. And that's one of the key problems is you don't need to compromise a switch or an EMC device or a network appliance device to get access to the data. You are playing with the protocol, the frame, the fiber channel connection. So it's not about root or admin, it's about the data itself. Also, if you're, depending on what kind of organization you are, HIPAA and SEC Rule 17A4 may require you to look at storage security. If you're an organization that holds medical information, HIPAA is very important to you. A default installation of storage area networks does not comply to HIPAA standards. If you're a financial institution, this is more of a vendor issue, SEC Rule 17A4 basically states that any data on the SAN cannot be deleted in an unauthorized way. So if you're a vendor, you have to make sure you have built that capacity into your product. So the importance of SAN security, what we see, SANs are very expensive and people are dedicating large amounts of data to these SANs. A Brocade switch, a MIC data switch, a fiber channel switch runs anywhere from $15,000 to $25,000 a piece. And you usually have 8 to 10 of them in a small environment. So they're not inexpensive devices. What we know, what the security industry knows, I would say, everyone in this room probably knows, is attacks rarely change, they get modified. So even though you might not have a good understanding of fiber channel as a medium of communication, you know about basic attacks in the IP world. And these basic attacks are the attacks that we're going to be applying to fiber channel. So I don't doubt by the end of this presentation, everyone in this room will understand the core issues about fiber channel security, because the issues are very trivial for the common security professional. And being that they're trivial makes it very important that we understand how do we start securing these items and not just leaving them as default. And what vendors know, I like this quote a lot. I read it actually online, and it kind of states what I think, what I'm trying to say. Falcon Store Software, they just make software for storage management. They don't make devices, they make storage management software. And the vice president was asked, what's the SAN security stuff? And basically said, there is no security, and that's why people don't talk about it. And I can't agree more. If you look at BugTrack, you look at CERT, how many issues do you see from Brocade switches, McData switches, Veritas, CA, all these storage vendors, storage software vendors, storage appliances? You definitely don't see a lot. Is that because they have better employees than Microsoft and Cisco, or is it that no one's concentrating in this market? Probably the latter. So the last slide in introduction, in my opinion, there's 3 core items in security that you need in any entity for it to be secure. Strong authentication, good authorization, and some level of encryption. Well, if you take those 3 core entities and apply them to storage area networks, you really have no authentication. Poor is, giving it more credit. Authorization is very average, probably a little below average. And then encryption, there's little to none. So if you combine those 3 aspects, you really have an uncomfortable environment for the data that you're holding in your storage area network. Yes?
Not that it's necessarily all that great, but authentication is handled at the application layer, what kind of additional layer authentication?
Yeah, good question. The question is that authentication, while it might not be great, there is authentication at the application layer when you talk about an Oracle database, and that is correct. That is correct. What I would be saying is the authentication within the frames themselves, from an HBA to a SAN switch, there is no authentication. But yeah, if you go to a layer like application, there is authentication you could do, but at that point, it kind of goes out of the Fibre channel world and back into the application layer. Good question. Okay, so at this point, we're going to start our Fibre channel overview section. I am going to try to go fairly quickly over this section so we can do the attacks. But if anyone has questions, again, please raise your hand because some of the concepts could be confusing, and it's important that we understand the concepts during this part. Fibre channel, as a technology, is very attractive. You can have speeds up to 2 gigahertz per second. It's very scalable and large access to data. So if you're a storage admin and you're thinking about IP, gigabit IP, iSCSI, or Fibre channel is very attractive because it can do a lot. And to say that it can go up to speeds of 2 gigahertz per second and do that in real time and be dynamic in nature is a lot of the requirements that most storage professionals are faced with. They're not faced with the security requirements, so that's why Fibre channel is probably a growing technology, and most storage area networks, again, are Fibre channel with some competition we will probably see with iSCSI. While the Fibre channel frames may be very attractive to storage administrators, they're all in clear text. So using any traffic analyzer, which is a sniffer, you can get all the information listed in this slide by looking at the frame. All this information in this slide is critical to attempt some of the attacks in the next section. So we all know enumeration, when you're doing an attack or an assessment, enumeration is a very important part of your assessment. If you can't enumerate enough about the targeted device, your attack will be very difficult. While in a storage area network, the enumeration phase is quite trivial because all the core information sits in the clear in the fabric. What I mean by fabric is a Fibre channel network. A SAN fabric has a lot of intelligence into it, unlike an IP network. So you can send commands, send requests, and get information back similar to this stuff that's going to be useful to you when you try to start guessing and attacking SAN switches and SAN objects. At the same time, and I think I've said this earlier, but at the same time, while the attacks are similar, sniffing in a Fibre channel network gives you more information, it's more complex. Fibre channel is a very complex technology, so it's not just you open up a software sniffer and start looking at the frames. There's a hardware piece that is required as well as a software piece for any traffic analyzer. So it's not something that's trivial to do or even, not complex. It's very complex. You're dealing about very, very fast speeds. but the basic idea is still the same. And we'll go over these terms in just a second, so there's no need to worry about those yet. In fact, we'll go through it right now. So here are some of the terms we're going to need to know for the presentation. We'll start from the top and work our way down. An HBA, host bus adapter, is equivalent to a NIC in the IP world. Simple as that. A LUN, logical unit number. LUN is basically a subsection of a storage array. So if you have a 300 gigabyte disk, you can divide it into 3 different LUNs, 100 gigabyte apiece, and name it LUN 1, 2, and 3. So when your file server or your database server is exposed to a certain LUN, they will only see LUN 1 because that's what you've assigned them to. Even though there's a 300 gigabyte disk there, they actually only see 100 gigabytes. And that's what a LUN is. Worldwide name, this is equivalent to a MAC address in a network interface card. The worldwide name is basically 16 characters, correct me if I'm wrong, but 16 characters that basically identifies the HBA on any client node in a fiber channel network. Name server. A name server is a table on a switch, on a fiber channel switch that basically takes a node's worldwide name, so from its HBA it has a worldwide name, takes the node's worldwide name and correlates it to a 24-bit address from the fabric. The 24-bit address is kind of like a DHCP address, if you will. And so it correlates the worldwide name to a 24-bit address. And then some name servers will also correlate that to what LUNs or what zones this client node has access to or belongs to. One thing about the worldwide name is the entity that identifies the node in a SAN fabric. You know, your worldwide name is your fingerprint, it's who you are. Your 24-bit address is used for routing. So that is what you use to route within the SAN from one node to the other. But to identify yourself, you use the worldwide name. So each switch will have a table that correlates the worldwide name to the 24-bit address of the SAN fabric. Zoning is just a logical segmentation of FC nodes on a SAN fabric. So if you have a SAN fabric, you could have 3 zones, an HR zone, an engineering zone, and a DMZ zone. Segmentation, similar to VLANs, not exactly like VLANs. We'll talk about how they're different towards the end. N port and F port, as I said earlier, fabrics are a little bit different and they have a lot more intelligence than an IP network. Every node in a fabric is assigned a particular type, either an N port, an F port, a G port, an E port, and the list goes on. What we're going to be concerned with is an N port and an F port. Most client nodes are N ports. Most ports on switches are F ports. Again, most, not all, but most. And then the last thing is floggy, is the fabric login. So when you connect to a fabric, a fiber channel network, what your client node will do is a floggy, the process of logging into the fabric and giving information and receiving information. This is important to know for one of the attacks we'll be talking about earlier. So any question on terms? I know I went through that quickly, but okay. Okay, here's some terms with pictures, because pictures are always good. On the left side, you see storage array. There's 2 disks there, and there's 8 LUNs. So that's what a LUN is. It's like you have 2 physical disks, but you actually have 8 LUNs, 8 categories to expose the data. In the middle, you see an HBA, looks similar to a NIC, and you'll see a worldwide name on the top, which basically is given by the manufacturer, so given by Brocade, QLogic, Emulex for each HBA. And then lastly, on the right side, you see a fiber channel switch, looks like, like any other switch that we've seen, and the name server, which correlates a 24-bit address to a 64-bit worldwide name. The fabric. We've already talked about the fabric a little bit. Again, it's the fiber channel network is the intelligent topology used for routing, naming, allocation, basically to get nodes communicating to each other in a very efficient way. The fabric has a lot of responsibility in a storage area network as opposed to an IP network where the network itself is controlled by devices. The fabric itself has a lot of information in a SAN. As I said earlier, each node in a fiber channel SAN, so if you have a database server, it will have a 24-bit fabric address just from the fabric. It will have a 64-bit worldwide name from its HBA. And it will probably be an endport, have the assignment of an endport, because it's a client node, a database, and it's going to connect to a switch, and the switch will be an F port, and it'll have an endport ID. And we won't get into that. That's for background information more than anything. So here's a nice little example, very, very high-level example of a fiber channel SAN. On the left side, you see two client nodes, and they both are endports. So that's an HBA there. And as far as the fabric is concerned, they're endports. And the HBA has a worldwide name. And you look down below, it also has a 24-bit address, connects to the fabric, and connects to the switches on F ports. Again, the fabric recognizes those as F ports. On the right side, you see a storage controller. The storage controller also has an endport and has a couple different LUNs. And at the top, you see the name server, which basically is the table matching everyone's worldwide name to their 24-bit address. So, our next example is a little bit more complex. Blue is IP and red is fiber channel. So we talked a little bit about defense in depth, and as you see in the IP world, or in the IP example, you have the internet, you have a firewall, then you have a switch with the two web servers, then you have another firewall, then you have an application server and a database server, then you have another firewall, and then you have the internal network. So you have 3 layers of security, very good defense in depth model here. But as you see on the back end, and this is not uncommon in a lot of SAN fabrics that I've seen at least. On the back end, you see that these web servers, these app servers, and the database server are all connected to the fabric for either storage, backup, or for dynamic content to each of these devices. It's not uncommon to have an entire Oracle database actually sitting in a SAN instead of locally on the disk. So it connects to a back-end fabric, and also you see devices in the internal network on the right side also connected to the fabric. And then while there might be some zoning there, and we'll talk about zoning a little bit more in a second, it's basically one big flat network where you're connecting a DMZ, an internet DMZ, an application DMZ, and the internal network to one big flat network. So the attack vector for an attacker would be one of the following two things. If you compromise that web server on the front end, you have some choices. You can either try to subvert that secondary firewall and compromise either that app server or that database server. And after you compromise that, subvert that third firewall, then you get access to the internal network, and then try to access some data from the internal network. While that might be possible, that's pretty difficult. You got to compromise a web server, an app server, subvert 2 firewalls, and then get access to the internal network. Well, what we'll show is that web server, once it's compromised, it is possible, it's not only possible, it's fairly trivial to use the SAN, use the fiber channel connection, and try to get access to that same data that might be sitting on that database server or even the internal network. So as an attacker or as an assessor or whomever you may be, the thing is your attack vector is quite simpler or smaller using the fiber channel connection. And if the fiber channel network is using default implementations, you'll see that it's actually easier to use the fiber channel network to get access to that data that you're looking for. So what is a fiber channel frame composed of? There's 5 different things. That's, again, more of a background slide. What we'll be concerned with is the header. That's where there's a lot of issues, at least that I've researched anyway, in fiber channel networks. Here's a structure of fiber channel. There's 5 different layers. Please do not think of the OSI layer because it'll just makes it more confusing. But there's 5 layers. Layer 2, frame protocol flow control, is the layer that we will be targeting and where most of the attacks that, again, I've researched are involved in. There's 5 different layers, with the higher layer 4 connecting to a higher level protocol such as IT and ATM and SCSI. So again, fiber channel layer 2 is the area where I have found the most issues, especially with authentication, authorization, and encryption. Again, authentication within the fabric at layer 2, there is none. Authorization parameters are weak. We'll talk about that in just a second. And encryption, again, Fibre Channel as a communication medium is not encrypted at all. Now, there are some things out there, some new vendors that we'll talk about in the conclusion section that you can use encryption, but again, a default installation of a SAN is all in the clear. So again, another background slide, Fibre Channel Layer 2. These are the items in Layer 2. What we're going to be concentrating most on is sequence management, the second bullet point, and exchange management, the third bullet point. That's where most of the attacks that we'll be talking about today are concerned with. Here's a slide or a picture of Fibre Channel Layer 2. If you see the header information, there's a source address and a destination address. That's the 24-bit address that I was talking about earlier. So the source address would be your 24-bit address, and destination would obviously be the 24-bit address of your destination. Then you have a sequence control number, the sequence CNT, and the sequence ID. Those two parts of the header field are in charge of session management. So between two nodes, session management is handled at those two areas. And lastly, exchange ID. Exchange ID is basically a way for two nodes who have logged into each other or who are trying to communicate to each other to tell the other how many frames they can accept at one time. So the exchange ID will say, hey, I can accept 10 frames at one time, so make sure you just send me 10. And the other node will say, well, I can accept 15. So that's done during the login process when two nodes are trying to communicate to each other. Again, I already talked about this slide. Okay. The best part of the presentation, Fibre Channel attacks. So we just finished the overview, and so this is where we will talk about the attacks and how to actually circumvent a lot of the issues in Fibre Channel. And I actually like to call them the attacks of mass destruction, because you're talking about a lot of data, and you talk about some destructive things you could do in a Fibre Channel network that is pretty trivial, to say the least. So within the attacks, we'll talk about 3 attack classes. Attacks on HBAs, which again are NICs, but for Fibre Channel switches, and then Fibre Channel frames. Okay, the first attack, spoofing. We also know what spoofing is, so I won't go into that. Is there a question? Okay, so spoofing. Basically, at this point, before I go into this slide, one thing I don't think I've covered enough is that the worldwide name in a storage network is the identity of the node. So if I'm a database server, my worldwide name is my identity. So when I need access to certain LUNs, to certain parts of the data on the storage area network, my worldwide name is the way that I get identified and the way I can be allocated the correct data that I should have access to. The problem is that the worldwide name is the only aspect that is used to allocate this data. So if you spoof a worldwide name, if you spoof a worldwide name, what happens? Well, there aren't no secondary checks. If you spoof a worldwide name and you've spoofed it to access a zone or a LUN masking property that you do not have access to, basically there's no backup, there's nothing to prevent you from getting access to data you shouldn't have access to. So your worldwide name determines what data you should have access to. If you spoof your worldwide name, you've basically subverted a zone property or a LUN masking property and received access to data that you do not have authorization for. So how do you spoof a worldwide name? Well, that's pretty simple. Most device drivers, most HBA drivers actually have that functionality built into their management console. So if you look at the slide, at the bottom of this slide, there's 2 different HBAs here, and both of them have the ability, they give you the ability. It's not something that they try to stay away from. They actually make it a functionality for you to change your worldwide name. In fact, if you look on the right side, if you can read that, it says change node's worldwide name. You just click on that button, and you put in the worldwide name that you want. And at that point, you've spoofed your worldwide name. And if you spoofed it to something that has access to a zone that you shouldn't have access to, once you reinitialize or reboot, once you reinitialize your node, you will be presented with data that you don't, that again is not allocated for your rights. Question? Yeah, very good question, or very good comment. There is a legitimate use for the worldwide name. Again, if you're a storage admin, you want to have the ability to change your worldwide name. So it's better to manage, easier to manage, easier to allocate, and you have your own convention. You don't have to use the manufacturer's, Emulex's worldwide naming convention. So this is actually a functionality. But thinking with your security hat on, this is something that is very difficult to swallow, because you're thinking about the entity that controls your identification, which is also the entity that basically is the only parameter to authorize you for data, and that thing can be changed very easily using the device drivers. So what does that mean? Well, if you look at our little example, you have two nodes on the left side. Node 1 has a worldwide name of 1117073, and node 2 has a worldwide name of 091276, and it goes on and on. I'm not going to put all 16 characters. So the Fibre channel switch has a name server on the right side, and it says the worldwide name beginning with 09 is in zone A, and zone A has access to LUN 0612. Or LUN 1 or LUN 2, whatever you want to call it. Worldwide name beginning with the number 11 is in zone B and has access to LUN 1130. So, using your device driver, the attacker on the bottom changes their worldwide name to 111773, reinitializes, reboots, whatever you want to do, and then connects to the switch, or is already connected to this switch, but relogs into the switch. The switch says, oh, this HBA has a worldwide name of 1773. Let me give them access to LUN 1130, which again is not the correct access. They've spoofed their worldwide name, or they've changed their worldwide name, and all of a sudden they're presented with data that they shouldn't be. Yes?
How does the attacker find out what worldwide names are available and proceed to that table so they can get back?
Good question. Good question. I'm actually going to get to that in about 3 slides, but let me repeat the question. How does the attacker get access to the worldwide name? It's a very good question, and I'm going to answer that in 3 slides. Another question. No, it doesn't. The question was, does the switch care that there's 2 nodes with the same worldwide name? Well, let me back up. It depends on how the switch is configured. Probably, in a lot of times, the switch will just update its information and saying, okay, this worldwide name now has this information, has access to this LUN. A lot of switches, again, storage devices are made for functionality and made for capacity. They're not really too concerned about doing error checking. They're concerned about getting the data to the right node as quick as possible. So once they see the request, they're most concerned with getting this data to this node. So what they usually do is just look at the request, and that's it. In fact, there's a feature that we'll talk about in like 10 slides, how you can enable that so you only look at the request, and you don't really look at what it's coming from or who they're accessing, or if they should have that access. So unfortunately, the switches don't do a lot of error checking. Any other questions? Back. The question is there any entities on the server level if 2 servers trying to access the same data? Is that correct? On the server level, no, because when you talk about the file level, because we're all talking about block data at this point, not file data. So when you look at the SAN, it doesn't get into those higher level protocols. It's looking at the block data, and the block data can be accessed by multiple entities multiple times. Next slide. And again, we're going to be going over these attacks at the end, so if you have questions after these slides, that's more than okay to interrupt. Switch zoning. Now, we talked about zoning a little bit, but it's a little bit more complex than what I've said. It's more than just a segmentation tool. Again, if you have a zone, you can have, again, an HR zone, engineering zone, and DMZ zone to separate out your nodes in your fiber channel network. Unfortunately, most zoning implementations, not all, most zoning implementations are based on worldwide names. And worldwide names, again, are items that can be easily changed and easily spoofed. So being that zones and LUN masking, which will be the next slide, are the two entities that are commonly used as security entities in storage fabrics. Being that zones rely on worldwide names, inherently you're relying on an entity that's easily modifiable, which is insecure. So the problem with zoning is that once a worldwide name gets spoofed, your zone properties, your zone allocation tables basically are subverted. The question is that the implementation of the vendors or the customers? We'll say both. And my next slide will say why I'm saying both. Zoning can be a complex thing. So one thing about the storage market or the storage industry is that there's a lot of confusion on even the definition of zoning. You know, Brocade might say one thing, McData might say another thing, Cisco might even say another thing, but there's not a lot of agreement. And unfortunately, the vendors have been kind of leading the market in the industry and not a standard organization. So when we say hard zoning and soft zoning, there's basically two types of zoning, hard zoning and soft zoning. They have different definitions, but we're going to go over the definitions that are predominantly correct, but at the same time, a lot of vendors have different definitions of them themselves. Anyway, hard zoning. What is hard zoning? It's enforcement-based zoning. So what that means is that if you have a hard zoning table with 3 nodes, the hard zoning rule will basically say these 3 nodes have access to each other, and I will go ahead and give them route information to each other. So if the 3 nodes are A, B, and C, I will tell A how to get to B and C, and I will tell B how to get to A and C, and so on and so on. I will give them that route information so they know where to go. And I'm going to look to make sure they actually go where they're supposed to go. So once A tries to access C, I'm going to look at that request and say, okay, A, yes, you have access to C, and I gave you route information so you know how to get there. Go ahead, move along, everything's okay. Hard zoning is very good. Hard zoning is very good. Soft zoning is information-based zoning. What soft zoning does is basically, again, you have one zone and you have 3 nodes, A, B, and C. Again, soft zoning will give route information to A to get to B and C, and B to get to A and C, and so on and so on. But if node A wants to access a different node in a different zone, soft zoning will not give that route to that node, but if that node knows how to get there, can set a static route, soft zoning won't deny it. It will just let it go through. So what does that mean? Well, soft zoning basically doesn't restrict anything. All it does is say, hey, I'm not going to tell you how to get there, but if you know how to get there, then go right ahead. I could care less. It's kind of like a good example I like to do is my phone book example, my phone number example. If you unlist your phone number from the phone book, does that mean people who you don't want to call you can't call you? Or does that mean that if I find out your phone number and I pick up the phone and still call you, your phone will ring? Maybe I didn't go to the phone book, so I didn't know how to get your phone number, but once I got it, I still can make that phone call. That's basically soft zoning. Hard zoning would be, not only can I not get your phone number from the phone book, but when I try to call you, it never rings, because you have a block saying this phone number is not allowed to ring my phone. Soft zoning, again, doesn't stop you from doing anything. So all those telemarketers can still call you regardless if you're unlisted. So you're probably asking yourself, well, hard zoning seems pretty attractive, so what are the issues? I mean, there's a good solution out there. And I think that's what kind of the question was. Well, and correct me if I'm wrong, if anyone knows a more, better statistical example, but I would say over 90% of the zones out there use soft zoning. And I would say every switch vendor promotes soft zoning a lot more than hard zoning. We'll talk about why in a second, but a lot of people don't even know that soft zoning doesn't restrict anything. A lot of customers that I've talked to, when I've talked to them about soft zoning and how it really doesn't restrict anything, that's really news to them. They're just not aware that it's not a restrictive tool. Again, it won't give out route information, but it won't restrict any node if it has statically routes or if it knows the route to a different node in a different zone. Now, within hard and soft zoning, there's two ways to set up zones, and that's based on ports or worldwide names. So port-based allocation for a zone is basically physical ports on the switch. You can say ports 1 through 4 are in zone 1, and ports 5 through 8 are in zone 2. So that would be port-based allocation for a zone. Worldwide names is using the worldwide name for the zone. So you can say worldwide name, 111773 is in zone 1, and worldwide name, XYZ is in zone 2. So you forget about the port numbers and you use worldwide names. Now, what do we know about worldwide names? It's an insecure entity to use. So if you use worldwide names for your zone allocation, again, you're using an entity that can be easily spoofed, so it's insecure. And unfortunately, again, 90% or so of the allocation for zones are based on worldwide names. Why? Because some vendors will probably tell you it's easier to manage and it's easier to set up and it's very dynamic, which is all true. If you have worldwide name zoning, if you unplug something from switch port 5 and plug it into switch port 13, it's still going to be in the same zone because it's based on worldwide names. It's very true. If you have a very dynamic SAN and you're changing things around very often, you need to use soft zoning. Otherwise, hard zoning is going to take a lot more time. But hard zoning, or port-based zoning, is restrictive. Again, zoning and LUN masking are the two security entities used. Zoning was not created as a security tool. It was created for a segmentation tool. And I think, most switch vendors would probably agree with that. They didn't create this solely for security. It can be used for security, but they really created for segmentation to help storage admins segment their fiber channel networks, not necessarily to restrict data. And I think that's obvious by soft zoning. Soft zoning is not a restrictive entity. So I don't think they really meant it to be a security tool. So zone hopping. So how do you commit zone hopping attacks? Similar to VLAN hopping, there's three different ways to do zone hopping. We'll just start from the top. If you have soft zoning based on worldwide names, there's two attacks you can do. One is basically you can spoof your worldwide name. So you spoof your worldwide name and then you subvert the zone table and you get access to a different LUN. The second attack would be maybe you don't want to spoof your worldwide name. What you can do is just get route information. And again, you probably ask, well, how do you get that? I'll cover that. But the short answer is from the fabric. But again, you can set static routes. And if you have static routes, soft zoning will not prevent you from accessing those nodes. Again, soft zoning won't tell you how to route to all these different systems. But if you have static routes and you have a script just to find all these nodes, soft zoning won't prevent you from getting access to those devices. So what about soft zoning based on port numbers? Well, if you have port-based zones, worldwide name spoofing won't work because switch port number 3 is in zone A. No matter what worldwide name you spoof, you're still going to be connected to switch port number 3, which is in zone A. So spoofing won't work. If you're using port-based allocation for your zones, spoofing will not work. However, if you're using soft zoning, the route attack will still work. So again, you could set a static route and still hop across zones that you don't have access to. The third type of zoning, which is hard zoning based on worldwide names, again, you could spoof your worldwide name and get access to a different node, even if you're using hard zoning, but the static routes, you would not be allowed to get hop across to a different zone with hard zoning, because not only is it not telling you the route information, but it's also checking to make sure that you're going to the correct zones. So it is doing that error checking that soft zoning doesn't do. Then lastly, hard zoning based on port numbers. There are no attacks, at least that I'm aware of, that work. That is the most secure way to set up your zones. Hard zoning based on port numbers. So again, you probably, or question? Can you repeat the? I'm not sure I understand the question. Can you repeat? Oh, okay. Yep. Okay, yeah, very good question, actually. The question is to subvert the last zoning method, hard zoning based on port numbers. You could compromise the switch and then change the zoning tables on the switch, and that is correct. Actually, my last section actually talks about how to do that. So very good statement. So let me back up. There are no attacks based on the fabric to subvert hard zoning based on port numbers. But again, if you get control of the switch, then there's a lot of other things you can do. Good comment. So here's our example. On the left side, we have a DMZ, and we have two nodes, could be two web servers or whatever, with a worldwide name of A and B. On the other side of the firewall, below is IP, and the top is Fibre channel. You have three nodes with the worldwide name of C, D, and E. So to commit a zone hopping attack, described in our last slide, again, you would have to compromise some server, some kind of access. That's definitely a default. Once you get access, let's say to worldwide name A, you would spoof it to C, D, or E, reinitialize and reboot, and the LUNs, the blue LUNs at the top, would be exposed to your system, even though you're in a DMZ environment. So the question that was asked earlier is like, okay, I understand that worldwide names are bad. You've convinced me of that, and I understand that anything that relies on a worldwide name, such as zoning, soft zoning, or worldwide name allocation, is bad. But how do you get someone else's worldwide name? That's what it comes down to. Now, that's a very good question, and again, it might be complex, but it's a trivial process. Worldwide names are 16 characters. So what happens is that in our example, we have 5 HBAs here with 5 different worldwide names. Most organizations, when they buy an HBA, they don't buy it from 5 different vendors. They're going to buy it from one vendor, right? You're either going to buy them all from Brocade, or all from QLogic, or all from Imulix, most of the time. So most vendors, in fact, all vendors have a certain set amount of characters that distinguish their worldwide name from other vendors. Similar to a MAC address. If you buy a 3COM NIC, it's going to have certain things in its MAC to identify that it's a 3COM NIC and not a Zercom or a Intel NIC. So same idea. If you compromise that web server with a worldwide name of A, you can see your worldwide name. They don't hide that for you. They don't try to protect that. That's something that you can get quite easily. So once you see your own worldwide name, you can guess that the first 8 characters or the first 4 characters or whatever are going to be the same for any other worldwide name, because you are assuming that they're using the same manufacturer. So if the entity is using a different manufacturer or has changed its worldwide name, that assumption would not work, but the most times that's not the case. So at that point, you can assume that you know some of the characters of the worldwide name. Going back to the phone number example that I started off the presentation. Even though I've not listed my phone number in the phone book, we all agreed that we would not use our phone numbers as our online passwords or our ATM codes. Why? Because it's still pretty easy to get. Same example here. Worldwide names, even though they're not listed anywhere, they're very easy to get from the fabric. So again, after you've compromised this web server, you basically send out requests to the fabric and start seeing the trends. Most worldwide names are in sequential order. So if your worldwide name is, 1000000, and then it'll be 9862, the next one could be 9872 or 9882. So you keep on guessing and you keep on guessing. The idea here is that you're not guessing like a password, because that could be that process could be difficult, but you're guessing characters, numbers, that you know are going to eventually be a matched entity for a worldwide name. It might take longer. Most of the times when you do this assessment, when I've done this assessment, it doesn't take very long, because either one or two things have happened. The default worldwide name from the manufacturer is left, and so you can basically guess the sequences all the way up, just like anyone's phone number. Or two, people have changed their worldwide names to be easier to remember, so they've just changed it to 1,000, and the next one will be 2,000, and the next one will be 3,000. So they've customized it to make it easier, but they've also made it easier for someone to guess. There's a question? It's possible to change the... Yes. The question is it possible to change the manufacturer portion of the worldwide name? The answer is yes. So getting a little bit into security by obscurity, and I will say it's that if you have your worldwide name and you do change it to something random, if we can use that word, complex and not guessable, easily guessable, you're going to be safer, but that's not to say someone can't figure it out. Again, same thing with the phone number example, is that eventually someone can guess your phone number. It's going to take a lot of time, but it's not something like a password that it's going to be, it could be any characters for any amount. It's going to be numbers, and it's probably going to be easier to guess. It's going to be a matter of time to guess that certain character. Question? Yeah, have I implemented it, or have I? I haven't. Yeah, the question is, have you tried or have you implemented brute force? And that is the attack that you basically do. You just, anyone who knows a scripting language, you can set up a script to keep on changing your worldwide names randomly and pattern-based, and basically once you've guessed a worldwide name, you reinitialize. Again, the process might take a long time, but again, would we consider our own bank accounts secure because it takes long for someone to get into them? Probably not. We want to make sure that item is not guessable. Question? Sorry, I can't hear you. I think I heard the statement. Basically, you can query the name server itself. Yeah. So again, the intelligence is in the fabric. So you can query the name server on the switch and get information about the worldwide names. There's some aspects where you can prevent that, but again, I think the comment, and it's a good comment, that pattern you can figure out relatively easily. And so that's basically what I'm trying to communicate, that being that you don't know the worldwide name, it's a very trivial process in the fabric technology to get that, and to get that relatively easily. So you probably wouldn't even have to go to the brute forcing, because you could use the name server and get that information from this Fibre channel fabric itself. Good comment. Question?
The name server is designed for the switch. So in example one there, the web server is compromised. There's nothing local on the web server that would enable those hackers to learn your worldwide name remotely. And that fabric is to secure your switch. Is that what you're saying?
Yeah, the question is, there's nothing local on the web server that would identify someone else's worldwide name, right?
Or even the local worldwide name.
No. So if you have compromised that web server, you will be able to see your own worldwide name instantly. Just like bringing up the device drivers, you can just look at your own worldwide name relatively easily, or there's command line utilities to do it also. But to get someone else's worldwide name, that's where you do the brute force, the guess factor, or simply just query the name server and say, hey, give me some worldwide names. And if you don't find the matching one, again, you can just do kind of a trend analysis. Another question? Yeah. Very, very good statement. We're going to actually get into that in the next slide. But again, we're thinking about, from the storage perspective, it's not about hiding information, it's about functionality. The comment was just made, which is another good comment, is a lot of storage software manufacturers or software vendors make tools for you to go out and get as many worldwide names on the fabric. So tell me all the worldwide names are on the fabric, and I will decide who I should have access to. Well, the point is that you can get a worldwide name relatively easily with, again, a lot of these vendor tools. It's not something that's hidden. It's something that is exposed on purpose. Good comment. Question?
So you say if you have to do the brute force method, then with 64-bit numbers, you're going to be thinking an awful long time and trying to brute force a number. But it seems like, I hear you saying that you just query.
Right.
Why would someone always just query? Why would anybody ever brute force?
Good question. The question is, with a 64-bit address, it comes down to 16 characters. Why would you want to brute force instead of just getting the name server, or getting the information from the name server or from vendor tools? It kind of depends. The reason why you would, because some implementations you can restrict that information to some degree. So brute forcing might be your only utility to attack. Again, that's probably the last one you want to choose. But if the name server is not giving up that information and the vendor tool is not being allowed to query the fabric, which is very uncommon, but let's say that happened, then you would have to use the brute force method. Question? Good question. The question is, do switches, fiber channel switches, provide logging when a name server or worldwide name has been changed? To be honest, I don't know. Does anyone here in the room know? No? Okay, answer is no.
You probably wouldn't have any way to detect if there was a brute force attack on worldwide namespace on that fabric.
Yeah, and that's another good question. Detection of these attacks is very difficult. Again, not only there's no logging, as the comment was just said, but again, we're dealing with speeds with 2 gigahertz per second. So if someone's trying to brute force, someone's trying to just spam the fabric, it's very hard to detect. There is no such thing as an intrusion detection system for a fiber channel network. Even if there were, you're dealing at 2 gigahertz per second. That's a lot of data that's going through the wire. So unfortunately, the attacks are very hard to identify. And I was actually talking to earlier to someone, no one's going to really have time or the capacity to view that something is being changed incorrectly in the same fabric, because there's so much data going across the wire at a given time. Question is, to query the switch, wouldn't you need some access to the switch? Besides a physical connection, that's all you need. And that's one of the major issues. That's where authentication is a huge issue. There is no authentication. So being that you're connected to the fabric, the technology, the industry recognizes you as authorized. It's a very good question, and it's kind of more of a theoretical answer that's one of the issues, is that there is no notion of authentication. It's like, oh, since you are connected to me and I'm a switch, you must have rights to access this information. Let me go ahead and give that to you. All right, why don't we go ahead and go on to the next attack. Next item, again, the second item in security is LUN masking. Again, LUN masking is more of a segmentation tool. But we know what LUNs are. Again, our 300 gigabyte disk, we separated into 3 LUNs, 100 gigabytes apiece. Now, if we have 3 file servers, you can say each one of them have access to one of the LUNs. LUN masking is just the notion of hiding the 2 other LUNs on that same big disk from a single file server. So just masking it off. A simple concept. There's 4 ways to do LUN masking, or 4 areas where you can do LUN masking. You can do it on the client itself, you can do it on the switch, you can do it on the storage controller, your EMC device, or you can do it from a third-party vendor, a third-party software product. All 4 of those can be subverted, and we'll go over how. The first way, the client node, is a very, very complex, it's not a complex attack. It's very, very trivial. And this is what you should be amazed, or maybe you're not surprised at this point, of how easy it is to bypass LUN masking. So if we're doing LUN masking on the client, basically, I'm a file server. I have access to this big disk. The disk is 300 gigabytes, but I only see 100 gigabytes, because that's all the space that's been allocated for me. Well, how do I change that so I can see everything else? So you just bring up the device driver. Again, if you're doing on the client, you have access to the device driver, and you see a couple things here. On the left side, you see the LUN information, the Fibre channel LUN information, and you see the Add button. You hit the Add button, and you add the LUNs you want to have access to. So as you see, we have access to 1, 3, 5, 7, and 9 in our example. You basically hit the Add button and say, I want to have access to 2, 4, 6, and 8. And then you hit Done, and all of a sudden, you subverted LUN masking. It's really that simple. What about the right button that says Disable LUN Mapping? Well, as someone mentioned earlier, there's tools out there to say, hey, this is all the LUNs that I'm aware of in the whole storage environment. Which one of these LUNs do you actually want me to expose to the operating system, and which ones do you want to mask? Well, you could say, hey, I don't want you to mask any. All the LUNs that you're aware of, just go ahead and present to me, and I'll take care of the rest. So same issue, is that you are controlling what you have access to if you're doing LUN masking on the client. So it's very easy to change. Question? Does hard zoning mitigate LUN masking? And the answer is no. Because hard zoning would be, no, because if LUN masking is done on the client, we're relying on the client's rights to the worldwide names and not the zoning properties. We'll still have zones, but the zones won't be the restrictive entity the LUN masking property is. But that kind of leads into the next slide, which, what if you're doing LUN masking on the switch, which is more common? How is LUN masking on the switch done? Well, again, it relies on worldwide names. So again, the same problem. If we spoof a worldwide name, by doing a spoofing attack on a zone, soft zoning based on worldwide names, which is also used for LUN mapping, you compromise the LUN masking properties also. So same attack, same idea, same process, same result. What about LUN masking on the storage controller? Oh, sorry, question. To my knowledge, on the switches that I've used, no. But again, someone correct me if I'm wrong. Port-based allocations usually used for zones. LUN mapping or LUN masking really relies on worldwide names and that only. And the reason why, there's a lot of new things coming out with these vendor products, so some of the latest releases might have they do have stronger security utilities, but the ones I've worked with are still using the traditional worldwide name allocations. LUN masking on the storage controller, again, your EMC device, same idea, based on worldwide names. You spoof your worldwide name, you have access to data that you shouldn't have access to. Same concept. Okay, so we're going to talk about two more difficult attacks, but one thing before we get into those is the trivial attacks that we just talked about, and I think we can pretty much agree they're quite trivial. Even though it's a complex technology, it's a trivial attack. The trivial attack gives access to data, gives you access to more data. These two attacks that we're going to be talking about are actually more complex, but end up with less data, which is kind of opposite. You would think that the more difficult attacks give you access to more, and that's just not the case, because the trivial attacks are easy and they get access to data right away. Anyway, the first attack, and I'm running short on time, so I'm going to kind of speed through, is session hijacking. Again, we're talking about 2 gigahertz per second, so this is very, very complex, but the idea is the same. In the TCP/IP world, we know session management is done by the initial sequence number, and if it's predictable in a TCP/IP packet, it can be hijacked. Well, what does it mean to be predictable? Well, if an unauthorized entity can predict the sequence, it can basically take over the session. Same idea in Fibre channel. The two items with in a Fibre channel frame that is in charge of the sequence is a sequence control number and a sequence ID. The sequence control number between two nodes that have an established connection never change. It's always static. So it could be 5 or I don't know, just some random number. Let's say it's just 5. So the sequence control number within the frame will always be 5. The sequence ID changes, but it just increments by 1. So again, if you're looking at the fabric and you see two nodes communicating, the sequence control number will always be static. The sequence ID will increment by the 1. So it's very predictable. So what you can do, similar to what we all know, is you can basically inject frames and hijack that session. Now again, you're talking about 2 gigahertz per second, so it's very complex. It's not as easy as a simple IP utility, but the idea is just as easy because the 2 items that are in charge of are very predictable. One static, again, one increments by 1, and so the session management process is very weak. The other attack is one of my favorite attacks. So addressing and routing, we talked about the 24-bit address that's used for routing, right? The worldwide name is used for node identification. So every name server on a switch has a table that takes the 24-bit address and allocates it to the 64-bit address. Well, that's similar to something that we use in the IP world that takes a routing address and matches it up to like a MAC, IP to MAC, which is ARP. We all know the problems with ARP, correct? Same problems with the name server. So what happens is that similar to ARP, you want to pollute the name server and give it a 24-bit address that does not belong to you, match it up with your worldwide name, your MAC address, and you will be able to receive frames that you should not be receiving, which is similar to the man-in-the-middle attack. So to go through this a little bit more technically, you're an endport. An endport commits a fabric login during the login process. We all talked about that. It goes to the address of all zeros. That's basically, it goes to the address of XFFFFE. That's like the broadcast address in the Fibre channel network. It has an address, a source address of all zeros because it has not received an address yet. Second bullet point, it receives an accept frame from the switches in the fabric saying, here's your new 24-bit address, use it, and now send me a ploggy, a port login. So I'm the node, I've just received a 24-bit address, so I send out a ploggy frame that says, here's the 24-bit address you gave me, and here's my worldwide name, go update your name servers, right? Because you want to have that name server updated. So when the switch sees as a ploggy frame, it says, okay, this is information that I'm going to use to update my name server. So I got the new 24-bit address that I sent that node and their worldwide name, and I update myself. I'm the switch. So what happens if you spoof or you modify or change your 24-bit address to a target's and use your own worldwide name? Well, if you modify it to be a ploggy frame, a response to an accept frame, you are telling it, hey, here's some information that you need to update your name servers with. Go ahead and do it. And similar to ARP, there's no authentication. So the name server will see, okay, I'm receiving a ploggy frame. I'm going to go ahead and update myself. I'm not going to verify it's correct, and I'm not going to see that that's the actual correct information that I should be receiving. So graphical example, number 1, node B continually sends out frames to the broadcast address. The ploggy address is used to update the name server. So of the 24-bit addresses of 1, let's just be simple, and the worldwide name, node B, the attacker has a 24-bit address of 2 and a worldwide name of 2. The attacker on the right side has a 24-bit address of 1 and a worldwide name of 1. You spoof or you send out a ploggy frame with a 24-bit address of 1, which is your target, and your own worldwide name, which is 2. You send it to the switch updates its name server, so when another entity wants to route to the target, the 24-bit address of 1, they're actually going to send it to the attacker because the name server thinks the worldwide name 2 has the 24-bit address of 1. I know that's kind of complex, but it's the same idea in IP. But here's the issue. Again, it's more complex. The dotted red lines are the part of the attack that is not working. So man-in-the-middle attack in a Fibre channel network has not been done completely yet. I'm not going to say it's not possible, but at the same time, you're talking about 2 gigahertz per second. It's hard to get a node or an operating system to deal with that kind of speed. But what I have been able to do is receive frames that I do not have access to by polluting the name server, but then again, sending those frames to the correct destination has not been working. So the true man-in-the-middle attack does not work at this time. So I'm running really close, so I'm just going to go ahead and just kind of blow through the rest of the slides. E-port replication. Basically, e-ports on a switch are uplink ports. They transmit information to each other quite easily. This actually happened in a real SSP where an e-port was modified, or an e-port on a customer C switch received the e-port on SSP and received all the zone information from a fiber channel switch. So what does that mean? Is that if you're using an SSP, you got to make sure that e-ports, ports that basically release all information about zones, are locked down. You can't have a dynamic changing on an F port from an E port because this customer of ours basically changed their node on the bottom half of the screen to a switch, and that switch received information of the entire storage fabric of the SSP, which is not ideal. I'm going to skip this attack. This is a denial of service attack. It's pretty trivial. It doesn't really cause that much damage, so it's going to skip that one. Web management, I just want to address this last issue. We talked about web management earlier. Basically, switches use poor passwords. Vendors are notorious always for using poor passwords. For some reason, fiber channel switches use very bad passwords, and I know you can't see this on the screen, but this is where you can get a lot of the name server information to subvert that last attack, where you can just start changing the zone information. Again, we've done this in an assessment, where you get control of the fiber channel switch, and you just put yourself in zones that you want to be a part of, because the password was brocade, McData, or was just blank. And at that point, you have control of the switch. You can give yourself access to anything you want. Conclusion. This is an important slide. Despite the attacks that we have reviewed, there are several mitigations. That's one thing. If you guys leave here today, there are a lot of solutions out there right now to basically stop most of the attacks we talked about today. Unfortunately, they're not used because the education's not out there, the vendors don't push about it, or the awareness is just not being communicated properly. Things like hard zoning, port-based zoning, port locking are things you can do today to start securing your networks. And I think I'm out of time, so I apologize. I ran super long. We only missed the conclusion section. We covered most of that during our presentation, but here's my email address if you guys want to talk after this, and some background information, and some special thanks to people who have helped me with this presentation. So thank you.